Okay, so this is lecture 5 for MOS transistor theory. So after talking about our device itself, we will move to the delay, but I think that we'll take maybe two or three lectures for this MOS transistor. Okay, then let's go to the previous review of previous lecture. So previous lecture was lecture 4. So in the previous lecture we have briefly talked about the CMOS fabrication, remaining one. So in lecture 3 we have thought about how can you make N-well. So after that we introduced many different steps to fabricate the MOS transistor. So maybe you remember the terms like self-aligned process. So self-aligned means that using the predefined gate step, we implant our source and source and drain is just formulated very close to this gate step. So that was self-aligned process. So that really helps us to make tight control over source and drain close to the gate step. So that was one of the things we have learned in our previous lecture. And after that we have thought about CMOS layout. Basically MOS transistor can be thought as just a cross section of these two things. One is diffusion area. So depending on your type, then sometimes you can have N diffusion or P diffusion, and also you have some vertically running line called as poly. So although this is not poly any longer, but anyway this is still called as poly, and the cross section shown here, that is regarded as channel of your transistor, and this is of course either source and drain, and also this is either source and drain. So therefore just having two lines you will have a MOSFET. So maybe you remember that this is the layout of 3 input NAND gate. So where can you find the 3 input NAND? In order to realize the 3 input NAND, so you have to serially connected triple N MOSFETs, and you can find it here. Here this is your ground, and this is your output Y, and here you can see that a transistor driven by the signal A and the one driven by B and the one driven by C, and this point are shared between transistor for A and B. Simply speaking, you can write it down. Here you have a transistor driven by A, and its one terminal is connected to the ground. So here you have another point, another diffusion layer, and this is corresponding to this point. And this is for this A transistor, this is one diffusion. However, for B transistor, this is also working as another diffusion. So we can see that yes, this is another transistor driven by B, and here we have another diffusion. So you can easily find that this is corresponding to a parallelly connected two transistors. Similarly, you can find B and C are serially connected too. So that's the reason why we have serially connected 3 transistors in pull down circuitry. So same argument can be applied to our upper part, and upper part was more interesting. So here you can see the parallelly connected transistors. So please review your previous lecture. After that, we have moved to the MOS capacitor. So after briefly discuss the structure of MOS, and eventually we have find this type of graphs. So when we have blue curve and green curve, they are corresponding to two contribution for negative charges required for this system. Since we are increasing the gate voltage, so in the substrate, anyhow we have to have more and more negative charges. But who contribute this negative charge required for this MOS system? So this blue curve is corresponding to the so-called depletion mechanism, and another one, green line, is corresponding to so-called inversion mechanism. In the case of depletion case, this is not related with increase of conductivity, so there is no free carrier involved. However, in the case of inversion mechanism, it is directly related to the increase of our mobile carrier. So simply speaking, we can postpone the occurrence of this inversion behavior by amount of threshold voltage. So when you apply a certain threshold voltage, then beyond this voltage range, now your charges are dominated by this inversion electron. However, below this threshold voltage, then actually you have no available free charge carrier, so it is not very suitable for current conduction purpose. So the positiveness of this threshold voltage is quite important for our application, because in this case we can clearly make the distinction between 0 volt and seemingly 1 volt or 2 volt like VDD. So in this case, we can clearly say that when we apply 0 volt, there is no free carrier. However, when you apply VDD, then we will have a lot of free carriers which are capable to carry charges. Okay, that was the essential part of this MOS capacitor. So 2.1 introduction is just repeating of this fact we have already learned, so I will quickly skip and we will move to the 2.2 related to the long channel behavior. So up to the second slide of this introduction, we have thought about MOS capacitor. So MOS capacitor is the vertical structure of our MOS transistor. So now we have MOS. By controlling the metal voltage called as gate voltage, then now easily control the number of charges beneath of this oxide layer. However, the current conduction through this line or this current path is perfectly isolated or prohibited because oxide layer is really a good insulated layer. So current conduction, although we can control the number of charges, but it is not a good idea to make this direct conduction. So instead of that, we wanted to introduce another path for our electrical conduction. So here and there, since these carriers are electrons, so we need to have some laser bars for electrons and here and there, and usually this part is called as source and this part is called as drain. Why they are called as source and drain? So in the case of an MOSFET, the contact which as the lower voltage relative to the other one is take the lower of source and drain. For example, if I apply 0 volt and 1 volt, then obviously this takes the lower of source and this takes the lower of drain. However, so when we say this is 1 volt and this is 0 volt, then which one is working as the source? So obviously the right one is working as the source. So please note that in the CMOS technology, actually source and drain are symmetric. They have the same structure. So only when only following the relative value of their applied voltage, the load of source or the load of drain is fixed or determined. Well, let's come back. Of course, so please don't regard this kind of symmetric structure as just granted. So we can find a counter example. For example, case of BJT. So bipolar junction transistor. In this type of transistor, we have asymmetric structure. So BJT case, we can find also similar things like this. Here we can find N-type region and another P-type region and eventually another N-type region. So without having this kind of MOS case, but here we introduce a certain terminal and here we have another terminal and here we have another terminal. So by controlling the contact voltage for this center one, then we can control the current path or amount of current between this N-type region and N-type region. So it is quite similar to the MOS system. So by controlling this center contact, center terminals voltage, then we can control the current. I mean that controlling the voltage of this center contact, we can control the amount of current between two terminals. So seemingly quite similar. However, from the structural view, so in the case of MOS, they have these two terminals have the same structure, so any of them can take the load of a source. However, please have a look at these two transistor called as BJT. Then here we have N-type region and here we have another N-type region. However, are they symmetric or not? So for example, this one is usually called as emitter contact and this one is called as collector contact. However, you cannot swap them. For example, I wanted to use this one as E and this one as a collector. No, this doesn't happen because they have different structures. Of course, they will work, but with different characteristics. However, in the case of your MOSFET, you cannot actually distinguish them when you actually apply the opposite polarity for your transistor. So please note that this symmetry is quite a peculiar point or feature of our CMOS technology. And yes, so by convention, source terminal is biased with low voltage. So we can, for MOSFET, we can assume that voltage of drain to source voltage is always non-negative value and body of an MOSFET is grounded. Why body of an MOSFET is grounded? So using the substrate tap, we make an intentional connection between our ground and p-type substrate. Okay, so this is all for structure itself. Of course, we have tons of things to be discussed. The actual form of MOSFET. However, right now we are just talking about the schematic one. So simply speaking, the main message of this slide is MOS FET. MOSFET is made by this MOS capacitor surrounded by two positive N plus regions called as source and drain. And this gate voltage control the number of electrons, and the change of number of electrons is sensed by this current. If we have no electron error, then there will be no current. And if we have a lot of electrons in between, then when we apply certain voltage difference between source and drain, then we will have a certain current. That is the main operation principle of MOS field effect transistor. Okay, so if you have any question, then please interrupt me anytime. So is more than welcome. So we will now talk about the operation regions called as substrate, linear, and saturation. So as much as I understand, so some of you already heard about this one. However, some of you have not. So that's the reason why I want to repeat this one. This is seemingly obvious one once again. So now let's go to that one. So the simplest one, however, in reality, very important one is substrate. When the gate to source voltages, it means that the voltage difference Vg minus Vs, this is defined as VGS and called as gate to source voltage. Then when this voltage is lower than threshold voltage, then we can easily understand here we have no charges, no inversion charges, no electrons at all. So in this case, the current would be quite small. So although that is quite small, I don't want to write down exactly in the equality sign. So instead of that, I want to introduce this similarity sign, and actually this is quite important. So in rough sense, we can say that, oh, if we have sub-threshold region, so the voltage region where gate voltage is lower than threshold voltage, then current is quite small. Yes, that's true. But how small is it? It really matters. It is really important. It does matter, and you have to be very careful about the amount of current. But for y, just treat it as 0 for this first order constellation. And when you go to, so previously we thought that, okay, threshold voltage is higher than gate to source voltage. So now slightly increase the gate to source voltage, and now it becomes eventually higher than what? Higher than threshold voltage. Then our MOS capacitor will provide us certain amount of negative charges here. Then, as I explained many times, so now we have good electrical connection between this source and drain. So now we have a capability to conduct electrical current. So we will have non-zero current, and drain current will be larger than 0, much larger than 0. Okay? So in both cases, so in both cases, this is actually the VDS equal to 0 volt case. However, when we apply high non-zero voltage for drain voltage, so since source is regarded as a reference, then it means that we have applied positive drain voltage, then we will have a lot of current, so that is written here. Think about it. Say that one typical example, threshold voltage is, for example, 0.3 volt. Well, then you have applied gate volt like 1.0 volt. Then what will happen? Please try to estimate where it is. Is this in its sub-threshold region? Certainly not. This is the voltage where higher than threshold voltage. So we will have inversion channel. So that is the situation. And now let's make a comparison between two cases. One case is VDS is exactly 0 volt, and another case is VDS is exactly zero point 0.1 volt. So please try to estimate the current conducted by this transistor. Do you think that this is higher or this one is higher? Which one current more conductive? Quite obviously, when you apply just 0 voltage, then actually even in this case your drain current becomes exactly 0, because you know this one just to make electrons, and the driving force of our electrical current is the voltage difference between this source and this drain. So simply I wanted to say that even in this case, when you have gate voltage larger than threshold voltage, but when you apply VDS equal to 0, then yes, drain current is exactly 0. So, are you with me? Then now we increase slightly higher voltage, like 0.1 volt, for example, or 50 millivolt. In this case, you can say that now this amount of electrons can contribute to current conduction, so ID will be 0. Then my next question is, okay, now you understand this is 0 and this is non-zero and a positive number. Then my second question is, how about this 0.2 volt? Please compare this and that. What will happen? Please compare 0.2 and 0.3. What you can expect is, since we have a conductive channel and since we are increasing the voltage difference across two channels, so maybe that is quite easy to understand compared with this 0.1 volt case. 0.2 volt case will conduct more current and increasing and increasing and increasing. You can easily understand when we increase the drain current, then we will have more current for this system. So everybody understand this one? Then let's keep this kind of discussion forever. So now we arrive at 1.0 volt. Happen to be we have this value, and let's say that we have further increased 1.1 volt. Then what is your expectation about the relative magnitude of your drain current? Which one will show more current? Of course, still you will have more current in the case of 1.1 volt. But my point is, from here to here, from point 1, point 2, point 2, point 3, we have relatively large delta of our drain current. However, now when we approach to this large value or high value of drain current, drain voltage, then this delta becomes quite small. So we have to make a distinction between this relatively low drain voltage case and relatively high drain voltage. I mean that, let me just draw something. I mean that this is y-axis is drain current and x-axis is drain voltage, and let's say that our gate voltage is already quite higher than our threshold voltage. Then what we can expect is when drain voltage is 0, drain current is 0. Good. And when we apply higher and higher drain voltage, then there will be certain direction of drain current. If you apply higher drain current, then you will have more current. That is quite obvious, increasing and increasing. However, what I wanted to say is that if you have applied already quite high drain voltage already, then even when you increase your voltage further, then the incremental drain current would be very small compared with the lower drain voltage case. That is my suggestion. So in this case, it is needed to distinguish these two cases. One case is just it behavior just like a register. So then there will be certain linear graphs in this case. After that, beyond certain values, then current is more or less fixed and doesn't increase much. So of course it increased. I want to say that it slightly increased, but compared with this steep behavior in low drain voltage, then this is almost constant. So this one is called as saturated drain current. So that's the reason why this part is called as linearism and this part is called as saturation region, depending on the behavior of our drain current, because drain current is the current we will use to drive other next gate. So are you with me? So this was the explanation about linear mode and saturation mode. So although here we have a certain criterion, we'll explain it later, but anyway, when we have a certain drain voltage which is higher than a certain criterion, then drain current is no longer increasing. So we will have just a fixed value or constant drain current, even when we apply higher and higher drain current. Okay, so we will revisit this one immediately with this long channel IV characteristics. So first of all, I wanted to say that what is the meaning of long channel here. Long channel means that what is long? Long here is related with the length of your gate. For example, think about this one. In many cases, you can see something like this. So if we take the lambda based rule, then in many examples you will find the smallest one, like smallest available our transistor. It has channel length which has the minimum size like 2 lambda and its width is 4 lambda, the narrow one. But anyway, here when we say that long or short, this is nothing related with our width. So this is not of our concern. The concern is related with this gate length. Okay. So let's say that instead of that, we have made 2 times a long one, like 4 lambda. Or we can make it any longer, 6 lambda, 10 lambda, blah blah blah. Anything can be drawn in based on this lambda. Okay. So in this case, these think about, for example, 20 lambda device or much longer. In this case, we don't treat it as minimum sized MOSFET. It is actually far longer than minimum sized MOSFET. So minimum sized MOSFET has gate length is 2 times lambda, but if we have 20, then it is much longer than the minimum available gate length. So in this case, we call it as long channel MOSFET. So are you with me? So for example, if you have 90 nanometer technology, then your transistor having gate length of 90 nanometer, or the case which is just a few integer multiple of this the minimum size, they are treated as short channel MOSFET. However, for example, 900 nanometer MOSFET, then whose gate length is 900, then in this case it is regarded as really long channel MOSFET. Okay, so I think that all of you are quite much with me. But I wanted to say one thing more. Let's say that gate length is 90 nanometer. Is it long or short? It doesn't make any sense without specifying the technology. So, for example, if we are working with 90 nanometer technology, then it means that, okay, then this is the minimum one. 90 nanometer is the minimum one. So certainly this is a really short device. But instead of 90, we are working, for example, 22 nanometer case. Then what will happen? In this case, it is far much longer than our minimum gate size, gate length. So this can be regarded as long channel MOSFET. So please note that what is long in this case really depends on your technology. So long means that please regard this long as just several times longer than minimum channel size available your technology. Okay, then there is something we have to care about. In digital scene, we are always using short channel device because we wanted to introduce the shortest devices to reduce our silicon area. So although we have to eventually consider the effect in the short channel MOSFET, but for why in this 2.2 we will talk about long channel IB. Okay, so are you with me? So once after studying the long channel MOSFET IB, then we will move to the short channel device. Then short channel device has some effects deviated from long channel MOSFET, so we will study that one maybe in the next lecture. Okay, So now let's go to long channel IV characteristics. So still we will say that gate source voltage is higher than threshold voltage. And of course, if we don't have such kind of condition, then we will treat this one as just a 0. But well, I will explain it later. So for a while, just to think about this condition. So now your transistor is beyond the threshold voltage, so you have inversion channel. So simply speaking, when we have this schematic, then here we have a source and drain, and since the gate voltage is higher than threshold voltage, we will have the charges. And now we know that qualitatively there will be certain current conduction, but our goal is now to quantify how large is it when a certain set of parameters are given. So more exactly, more specifically, we wanted to calculate DC. Express our drain current in terms of gate voltage and drain voltage. That is our goal, and we will do this one in this lecture. I think that was already covered in the microelectronics course, but we have to repeat once again. So our goal is to calculate current. Yes, and this current is given by two factors. So proportional to what? Number of carriers, charge carriers, and speed of carriers. We need these two factors. So by multiplying these two factors, we will get the current. Then, and of course, as I told you before, the most important thing in this control is of course the number of charge carrier, and number of charge carrier was controlled by our gate to source voltage. So first of all, let's think about this one. The charge in the channel region is given by this form. So piecewise linear behavior. So when we have a certain threshold voltage, and if our voltage across gate terminal and channel region here and there is beyond threshold voltage, then we will have just a linear capacitor, and that linear capacitor is given by this Cg. And of course, below that value, threshold value, we have no charge carrier. So we have already seen it several times. For example, in the case of our green line, so maybe you have seen it before, right? Yes. Now you have this kind of piecewise linear graph. So this is really good approximation for our transistors inversion charge density. So beyond a certain voltage, then now we will have the inversion charges. So now we can say this way. And of course, we have a certain, let's say, here we have a certain slope because this is a linear behavior, and this linear behavior is given by gate oxide. So if we have higher gate capacitance, then we will have quite steep behavior. And if we have relatively low gate capacitance, then we will have relatively smooth transition from more moderate increase of our inversion charge density. Then which one is more preferred? Of course, higher one is much more preferred. We wanted to have um, a really steep behavior. So below threshold voltage, we don't want to have inversion charge. However, beyond threshold voltage, we wanted to steep increase of our charge density. So therefore, the desirable one is a gate capacitance higher and higher. Please note that in the textbook, so it was written as in this form, and this is actually charge density. So it charge, so it should be electron has negative charges, so actually it should be on negative value. But however, when you write down in this way, please understand the absolute sense. So minus sign is understood. Anyway, let's go this one. Then gate capacitance. How can you obtain this gate capacitance? So Cg here shown here itself is really have the unit or dimension of capacitor. So we have farad in it. Then how can you estimate this farad? Then this is given by this form. So C ox multiplied by W and L. What is it? Since we are working with this MOS capacitor here, MOS capacitor, the capacitance of gate is dominated by this oxide layer. So since we have oxide layer, from this one we can consider the farad per unit square. So unit area. So area capacitance can be calculated, and by applying the area of channel region, then we can calculate this one contribute another square centimeter. So they are cancelled out, then we will get eventually the error. I mean that, think about this one. Now you have the minimum sized transistor 2 lambda and 4 lambda. Then you will have a certain gate capacitance. Then instead of that, now I have introduced 2 times wider transistor. Let's say that this is now 2 lambda times 8 lambda. Then when you draw this 2 times wider transistor, then what will happen to your C ox and C ox, and what will happen to your CG and CG? In the case of the same technology, CG is nothing related with this size of your transistor. In this case, they are the same. So oxide capacitance is, although that is written as oxide capacitance, but it is not in farad unit, but that is written as farad per square centimeter. And this is just technology dependent parameter, not area dependent. However, you know, this gate capacitance is actually the capacitance multiplied by the area. So now we have twice wider area than this minimum sized one. So we have to say that when we multiply twice of this original one, then we will have the gate capacitance of a wide one. So are you all with me? So if you have 10 times wider, then you will have 10 times more gate capacitance. However, that is just scaled by its area. Then I wanted to ask you some question. Previously here, you have this flow. Your channel charge is given by Cg times gate overdrive voltage here. Then in this case, you have, for example, you have introduced 10 times wider device. Then you will have 10 times larger gate capacitance. So you will have 10 times more channel charge. So that is quite obvious. It means that if we introduce 10 times wider device, then we will have 10 times more charges in it. Here we have, let's say, the Q, and now we will have 10Q. Wow! But is it really good or not in terms of the capability to collect electrons? You can easily understand. Although this one has 10 times more charge, but it is only possible with 10 times wider space. So if we take a unit space, unit area taken from here, and unit area taken from here, per area, the capability to collect electron is the same. So with me, although you can easily change your gate capacitance, however, per area, the capability only determined by this Cox. So it is important to increase Cox itself. Otherwise, although you have a wide one, but still when you apply same gate voltage, your channel will have the same areal density of your electrons or holes. So in order to increase the areal density of your electrons, you have to increase this oxide capacitance, and this oxide capacitance is simply given by the inverse of oxide thickness. So if you have thinner and thinner oxide, then you will have larger and larger density, higher and higher density of your electron charges. So are you with me? Let's say that, for example, your gate source voltage minus Vt is happen to be, for example, 0.3 volt, and you have decreased your oxide thickness from 4 nanometer to 2 nanometer. Then what will happen? Then simply speaking, when W and L are fixed, then you will have twice more aerial electrons for this oxide thickness when you have the same gate overdrive voltage. Because since the thickness is twice shorter, so your oxide capacitance becomes twice larger. For same gate overdrive voltage, you will have twice more charges. So you can easily understand, due to this kind of estimation, always people are trying to decrease its or their oxide thickness. Okay, so are you all with me? Importance of oxide thickness is explained because oxide thickness actually determines oxide capacitance, and this oxide capacitance determines the capability to collect electrons and holes beneath of this oxide layer. Then why don't you just make a simple exercise together with me. So for calculation purpose, I have prepared a Python window here. Yes, so this is our exercise. Let's try to calculate the oxide capacitance COX, which has the unit of farad per unit area when the effective oxide thickness is 1 nanometer. Then how can you calculate it? So that is given by permittivity of oxide. So permittivity of oxide is written here, epsilon oxide divided by oxide thickness. Then let's do it. So here you can see that this is the epsilon oxide. What is it? This 8.85 times 10 to the minus 12, that is corresponding to the vacuum permittivity. And instead of a vacuum, we have the silicon dioxide as an insulating layer, so it has relative permittivity of 3.9. So by multiplying this one to vacuum permittivity, now we have the permittivity of our oxide layer, and this is corresponding to epsilon ox, and it is divided by what? 1 times 10 to the minus 9. This is the 1 nanometer written in our SI unit system. Then that will be the capacitance, so COX. But please note that all of them are calculated in SI unit. So this is farad per meter square. So now we are applying this kind of thing, 10 to the minus 6 times 10 to the minus 6, and this is corresponding to 1 micrometer and 1 micrometer. So simply speaking, if we have 1 micro by 1 micro system, if our channel has 1 micro width and 1 micrometer length, do you think that in these days this is large or small? This is really humongously large device. In this case, what you will get is 3.5 times 10 to the minus 14. So this is corresponding to femtofarad. Okay, so this is the value of this transistor. And nowadays, how small is it? So at most you have just several times of 10 nanometer, also several times of 10 nanometer. Let's just say that, for example, having just 100 and 100 nanometer, already that is 10 times smaller and 10 times smaller. Are you with me? Compared with 1 micrometer, 1 micrometer, then in this case your gate capacitance will be 100 times smaller, so you will have more or less 3.4 femtofarad as what? As the gate capacitance. So that is a farad itself. Okay. Since our transistors are so small, therefore related capacitance itself is extremely small in these days. Then now let's go to this one. Once again, we wanted to calculate current, and we have thought that, okay, current is proportional to the charge density, Q channel, that was shown our previous one, and it has something like some charge Q. So this is Coulomb. So we wanted to introduce also speed over our electrons. So we wanted to introduce certain values which has the form or unit of second, centimeter per second. So that is required for our calculation. So you can see that, so although I will not consider this one in this course, the speed over our transistor or speed over our electron can be written as this form. So one is the quantity called mobility, and another one is quantity called electric field. Then let me just consider their units. In the case of mobility, it has its unit like volt per second. So maybe at first glance it is difficult to remember, but please try to remember it. This one has this kind of behavior. So square centimeter per volt second. And what is the unit of your electric field? Your electric field is the potential divided by the length. So potential divided by the length. This is your unit system. So let's try to make the product between these two quantities. Then you will find that this centimeter is eliminated and this volt is eliminated, and you will have eventually centimeter per second quantity. So now you understand mu times mobility times electric field will give us the electric so speed over our carriers. And here we make certain things like this. Now we have channel potential, and channel potential can be derived with respect to the channel position. Here x start from 0 to Lg, x equal to 0 and x equal to Lg, and this x equal to 0 is assigned to our source terminal, and Lg is assigned to our drain terminal. And any point in between, then we can think about the electric field, and this electric field can be obtained by the first derivative of our channel potential. Then now consider this product, the Q times speed. Then how does it look like? Then without many leading coefficient, we will have something like this. We have VGS minus VT. So also, this is the one terminal wise, but please have a look at it. Then now we have the difference between VG reference to C channel. So now write down in this way. Now we will have, instead of that, we will have VG minus VC minus VT. This is nothing but this is VGC multiplied by our speed, and speed is given by this form. Here we have mobility, and here we have dVc over dx. Now you can see that from the viewpoint of internal quantity Vc, where can you find the Vc? Now you can find here Vc and here derivative of Vc. So are you with me? So from this one, please once again, what is the physical meaning of this expression? This expression just shows that this is number of your electrons, and this one says the speed of your electrons. So then this expression will give us two terms, like The first term is the linear to Vg minus Vt times dVc over dx. So are you with me? Taking this one, and another one, you will have this form. And we have another one, like Vc times dVc over dx. This is 1. And when we integrate it over, starting from 0 to Lg, then what will happen? This is just a constant. Then we have to perform the integration of first derivative. Then we will get just the difference of Vc evaluated at Lg and Vc evaluated at 0. This term will come. And how about this one? In this case, if we integrate it, then we will have half of squared Vc evaluated at also Lg and x equal to 0. So are you all with me? Simply speaking, I wanted to say that this one, drain current is given by the channel charge and speed. But everywhere inside is this device, since channel potential is position dependent, so they can have their own channel charge and their own speed. Here we have a different charge density and also different speed. But anyway, the product between them, this one gives us the current and this one gives us the current, and these two current component should be identical regardless the value of x value required for our calculation. So that's the reason why I wanted to make just integration over x-axis and divide it by L. So we just take the average over a constant value. So
적분했을 때 이게 되는 게 이해가 안 되거든요. 이거 적분했을 때 이거 되는.
So your VC, you have dVc over dx, and this is nothing but just dx of Vc square. Okay, so therefore that's the reason why you have not just half of Vc, but you have half of Vc squared here. So now you have these two terms. So you will immediately understand your current will have two terms. One term is just linear to your potential, and another term is the quadratic to your potential. So now when we finish all of this intermediate calculation, then you have this linear mode expression for our current. Please have a look at it. Here you can see that the first term, which is linear to your potential, where can you find it? So this is constant and this beta is also constant, and you have VDS. So beta times VGS minus VT times VDS. This is the linear term you have. Another one, you can find something like this, half of beta times VDS squared. And what is the origin of this term? Second order term. And second order term was taken from this one. So are you all with me? So simply speaking, this linear expression was obtained by considering the product between channel charge and its speed written in mu times electric field, and by integrating this ID component over any evaluation point like dx and taking the average by taking this LG, then you will get this linear expression for your MOSFET current. Okay. So of course, some of you are not very happy with this kind of brief description about derivation. If you are interested, please refer our full discussion about our drain current expression. Anyway, you have this form, and now let's go to the higher and higher drain voltage. Here you have two competing terms like a linear term and quadratic term. If we increase drain voltage, of course this linear term increase. However, also you have to consider here we have decreasing component, here taking minus, and if you go to higher component, and this one, the first term increases linearly, but this negative term also increases in its magnitude quadratically. So eventually you can find that this will draw in such kind of graphs. Oh, sorry about that. This is important, so I have to make beautiful graph here. VDS and ID following this linear mode expression, then we will have at first line like a straight line like behavior, but eventually this second order term will dominate. So we will have eventually arrive certain point where we have no longer increase in our drain current. Okay, so please try to find out that point. What is the condition for this? Here we have increase of ID with respect to VDS becomes 0. Can you find it? So let's do it together. Just taking the first order derivative over our ID with respect to VDS, then we will have beta times. So this one is first derivative derived, then we will have just have VDS plus beta VGS minus VT minus V half over VDS is given here. And when we have that is equal to 0, then this beta can be eliminated, and this condition is satisfied when VDS equal to VGS minus VT. Simply speaking, when your drain voltage reaches at the difference between gate voltage and threshold voltage, so-called gate over drive voltage, then you will reach the vanishing gradient of your ID current. Of course, we can try to apply this expression beyond this point, which is given by VGS minus VT. However, that will give us certain kind of quadratic decrease in this case. This is not physical at all, because when you apply higher and higher drain voltage, this model just predicts that your drain current is now start to decreasing. It's not. Actually, it is just saturated. So, therefore, in our simple expression, we have to introduce some limit of this linear mode expression. Okay, please apply this linear mode expression only when your drain voltage is lower than this gate overdrive voltage. Then you will have this behavior, and beyond the gate overdrive voltage, when your drain voltage is higher than that, then please just use saturation current value. Which one is this? Oh, how can you decide this saturation value? It's simple. Just in order to make the continuity of our drain current, insert VDS equal to gate overdrive voltage. Then eventually you will get this expression. So of course here we have the leading coefficient, and the leading coefficient is simply given by mu times C ox W and L that was given here. Okay, then let me just try to estimate. Here I have prepared one simple thing. Here, calculate drain current when gate voltage and drain voltage, both of them are 1 volt, and W over L is 2. It means that maybe we are talking about the minimum sized one, and oxide thickness is 1 nanometer, and mobility is 80 square centimeter per volt second. And let's try to calculate it. So how can you calculate this one? I will just write down the expression. So evaluation is your stuff. So in this case, we first calculate the beta. So 80 square centimeter volt second, and also we have to calculate Cox. Cox is 3 times 9 times 10 pound 8 10 to the minus 12. So this 12 is farad per meter. So when you take the centimeter scale, then please use this centimeter and minus 14. Anyway, so also you have 1 nanometer here to evaluate your C ox value. Then what is remaining? Yes, you have a W over L, although you have no specific number for L and W, but it's okay because we are using this ratio W over L. After that, once you get the beta value, then please consider whether that is in saturation mode or linear mode. How can you determine this one? Since gate voltage is 1 volt and threshold voltage is 0.3 volt, we can say that gate overdrive voltage is just 0.7 volt. Then compared with drain voltage, which one is larger? Drain voltage is larger, so now our system, our transistor is in its saturation mode. Then we have to apply the expression for saturation mode. So simply speaking, 1.0 volt minus 0.3 volt and its square. That is used for our ID calculation. So are you all with me? So this is just done, and however I wanted to say that this is a simple evaluation, but in actually when we characterize our IV characteristics, we always have to care about two things. Two things is that one, the first one is input characteristics, and another one is output characteristics. Okay, unfortunately time is up, so I have to stop here, but please please have a look at our PPT material, PDF file material already distributed in our GitHub, and I will continue to discuss about our input characteristics and output characteristics. Both of them are quite important, and I will show you how can we read these graphs in the next time. Okay, do you have any question on the today's lecture content? Oh, so sorry about that. Then you have homework, your first homework, very first homework. So now please submit your homework. This is just a drawing problem. Please draw your input characteristics and output characteristics. I think that already you can do it with given expressions, equations, and please do it for me. Okay, then you must submit it through our GIST LMS system. I will upload the homework problem, and the due is the day after tomorrow, before our lecture start. So you have just 2 days. So this homework is quite simple. So I hope that all of you can do it within time limitation. Okay. If you don't have any question, then I want to wrap up today's lecture. Thank you.